This is chapter 16, lecture 21 and 22. These are the slides for both, although we won't go through the full lecture. This would technically be the lecture we'd have on Wednesday and probably Friday had I been there. So we're a little ahead of time with these async lectures just because of the time constraints of a 50-minute. So I want to go over a couple of things, and now a little different. I don't have the slides and a way to write at the same time. So I'm going to go over the first couple of slides, talk about them, and you may have to go back and look at them, and then I'll do a little bit of drawing to kind of overview it. Now, again, remember chapter 16 is all about F equals ma. So it's F equals ma of rigid bodies. And so part of that is the difference between this and chapter 15 is now we're finding reactions. So for example, we look at here, we've seen the upper picture before with the sliders going, 1B going down and A going right with omega or alpha. Only now we're actually adding to it the center of gravity's acceleration. So acceleration of x and in the x direction and in the y direction, something we didn't really deal with in chapter 15. And so we can model that as a FBD and a kinetic diagram in the lower picture showing the reactions and forces, the sum of the forces, and then equaling to the I alpha plus the respective mass times accelerations. Now, the good thing is that these problems are solved pretty much the same way as what we did in 16.1. The reason we call it constrained is that now, instead of it just rotating freely about its center of gravity, we now have a actual point that we control it by. So for example, we have a rivet or something that is holding the structure in place. So if we look at, for example, this, we see that in this potato here with G in the center is actually pinned at O, so that G acceleration, both its normal and tangential, is all related to O. And so from that, we get this, which is again saying that if we sum all our forces about G, then that's going to equal our I alpha and our MA. Now, this slide in particular is important. So let me, and it may help to stop and go back and look at it, but I'm going to go ahead, stop the share. And now let's look at this from a drawing perspective. So really what we're saying is if we have our potato, then we know that if this is the point that it's connected, let's say it has some kind of a bracket that's holding it. All right. So that's going to have a reaction. Hence the R and the X, R and the Y. And in addition, it may have forces acting on it. So F1, F2, F3, and so forth. So what we know is the way this is going to react is like before, is it's going to pretend that's the same potato. It's going to, you're going to have your G here, but remember that when this wasn't constrained, then we would draw a vector from G, and then we would also have a rotation. Well, now the only difference is what we're doing is we still are looking at the respective rotation, and this would be the mass times the acceleration in the tangential, mass times acceleration in the normal, or sometimes referred to as x and y, depending on your coordinate system. And in additional, you still have your I alpha. So what does this mean in terms of an equation? Well, here you're still going to write the sum of the forces, I'm sorry, the sum of the moments about R is equaling I alpha plus MAD perpendicular. Okay. Now, in the case of this acceleration here is based on this distance between G and there, and that's our R. So notice it's the same equation applied the same way. The only difference is now we're constrained. So we still have this relationship, and we still have the relationship where if we sum the moments about G, we just have I alpha. And The difference too is that now we can sum the forces in the x and say that's going to be max, and sum the forces in the y and give us may. So we haven't created anything new. It's just a kind of rebranding of what we've done before so that we can solve problems that have a slightly different constraint system. Now, I know at first when you see it, it'll seem strange, but trust me, it makes more sense as we look at some examples. Now, if we look at our next slide, and you can see that in this case, we have a 24 kilogram plate. And if we release the plate, what's it going to do? It's going to rotate. And so this really looks like this from a free body diagram. You have the reaction AXAY, you have G, and then you have the respective acceleration, one going back towards the center and this going this way. Now, notice how it says mass times acceleration normal equals 0. Well, the reason for that is because when you first release it, omega is 0. So there is no omega squared r term. So what we're left with is just simply Ig alpha plus MAR. And that, of course, is always going to be our tangential acceleration. So what I mean by that is, in this case, if this is 0, then this will always just be MAD perpendicular, which we know can be also written as mass times r squared times alpha. And so that we can consider our tangential acceleration. Now, if we look at, and I'm not going to do this example because I have one exactly like it, I want to show you. Looking like this. Now, in this example, we have, and I would take at this time, pause, write down the information you have, and then come back. And in fact, if you know how to do this or want to make an attempt of it, more power to you, because that the best way to learn it again is practice. Okay, so I'll assume you've paused it, you've written it down. So we have something like this. Stop the share. And there's our crate. All right. Now, we go ahead and put some information on our crate. Okay, so here's a better drawing. Now we see that our box, we know that the mass is 80 kilograms, and we know the dimensions. All right. Now, so if we think about this, first thing we'll probably want to know is the moment of inertia. So it turns out that for any box or rectangle, I is equal to 1/12 m a squared plus b squared, where a and b are just the sides of the rectangle. And so as you can see, unlike in the area moment of inertia, the mass moment of inertia is not, it doesn't matter which you make as a and which you make as b. So if I plug in the respective 1.2 and 0.5, which I know you can do, I get 11.267 kilogram meter square. So now I have that. All right. Now, you notice that I've drawn my free body diagram down here. So just like before, you have our weight and this our reaction E. And then here we have I alpha and then the acceleration center of gravity. Now, even though it's constrained, meaning that when we release it, it's going to pivot around E, we still look at the acceleration of gravity. We don't look at the acceleration of E, well, because obviously E doesn't go anywhere, it's just a point. So the only difference is now we're taking our moments with respect to that static point and looking at how they how that point's distance affects the moment created about G. Okay, or I'm sorry, not the moment about G, the accelerations of G. Okay. Now, if we look at the r distance, because remember, what's our equation going to look like? It's going to be the sum of the moments about E, and I'm going to make clockwise positive because of the way that it's set up. And that's going to equal I alpha plus MAD perpendicular. So what's my D perpendicular? Well, that's going to be, as you probably guessed, this distance here. It's going to be this horizontal distance, okay, because it's perpendicular to the acceleration direction, right? So if I draw a right triangle, I have this and this. So I know this side dimension up to here, that has to be 0.25, half of that. And I know that this dimension, if this is 0.6 to the middle and the whole thing's 0.85, that this dimension also has to be 0.25. So the whole thing's 0.85 minus 0.6 gets that. So we have a right triangle. So the hypotenuse, the distance we want, is 0.354. Okay. So now that's what we're going to use for our D perpendicular. So if we look at our sum of our moments, what do we have? Well, the only thing is the weight. So it's going to be the weight times 0.25, right? Because that's that distance and the weight's straight down. And that's going to equal I plus mr squared times alpha. Remember how we say acceleration is r alpha, D perpendicular is r. So if we substitute those here, that's what we get. And again, it's just the parallaxis theorem. So now we can plug in numbers, 89.81, 0.25, and that's going to equal 11.267 plus 80 times 0.354 squared, which we know is also just 0.25 times the square root of 2, right? For right triangle. And then all of that times alpha, okay? So now we get alpha, and it turns out to be 9.21 radians per second squared. There's our value, 9.21. All right. Now remember, what did it ask in the first place? It asked what's the angular acceleration of the crate. So we got that. But it also, and that's how you know it's a chapter 16 problem, what is the reaction? So that's how you differentiate. With chapter 15, there'll be no forces, no reactions. Chapter 16, there will be. Okay. So now we have to look at what does the uh, what does the acceleration in these directions tell us? Now, one thing we know is that the acceleration normal is zero. As I said before, omega equals zero at instant, right? That's the instant you drop it. So no, none of that. So really, if we want to figure out our reactions, we have to sum the forces in the X and the Y and write them out like that. So go ahead and try based on what you know, and then we'll solve. So now you've paused and you've done it. Good. So let's check it. Now remember that if you're summing the moments in the X, we have to figure out what that force is, or I'm sorry, what that acceleration is. Now, we've determined that if that's the acceleration point, then it's going in this direction. That means that acceleration in the X is going to equal acceleration tangential times cosine 45 degrees, and acceleration, sorry, going down here in the Y is going to be acceleration tangential sine 45 degrees. Now, how do we get this? Well, we know that acceleration tangential is just equal to r alpha, which if we go ahead and um, multiply by our distance, it's just simply going to be 9.21 times 0.354. Okay, that's what that is. Sorry, it's a little small, but that's what that. So if I go ahead and write it out, what do I have? Sum of the forces in the x. Well, the only force in the x is E. So EX, what does it equal? Equals the mass times um not gravity, sorry, times the 9.21 times 0.354. So that's our alpha times r, right? Which gives us that. But in order to get that, we have to then also multiply by cosine 45 degrees. So when all the smoke clears, we get 184.4 newtons. Okay, and there's our answer. So y is the exact same process, except you have to, of course, count for gravity. So EY equals, and so that's going to be what? We're going to assume EY is up. So if we sum the forces, we're going to say EY is the force up, and then it's going to be minus 80 kilograms times 9.81. And then that's going to also be equal to, now the acceleration in the y is negative, so we have to put a negative sign there, right? Because we've defined it as going down. So we'll say equals negative, and that's going to again be 80 kilograms times 9.21, 0.354 sine 45 degrees. All right. So we end up with EY equals 600 newtons. All right. So, and if we think about if it were static, it would be 80 kilograms times 9.81. And so if there would be no x, so if it was static, right, EX equals 0, EY would equal 9.81 times 80, which if we round that to 10, that's about 800 or about 780 newtons thereabouts. So definitely much greater than that. And that's why we expect that, because the crate's falling away. And so there's a lighter load here. All right. So I hope that makes sense. Um, I want to do another example that looks similar to this. And then we'll do a longer example that's a little stranger. And then we'll save the hard example, the really hard examples, for Friday's class. Now, go ahead and share. All right, so here we have this long, slender bar, and we're given the length 900 millimeters, mass is 4 kilograms, suspended from a hinge at sea, so on, so on. So you can go ahead and draw it, put the particulars down. And similar to what we did before, we want to find alpha and the reactions at sea. So very similar problem to what we just did. Hopefully, if you understood the last one, you should be able to do this one on your own. So I would go ahead and attempt it as far as you can, and then click back in to get the solution. All right. So here's what it should look like, right? So I have L over 2, L over 2. There's R bar from point C. R bar is just, again, our perpendicular distance that we define. The reaction CY, CX, this here being our mg. And then we have mass I'm sorry, the mass times acceleration A. Sorry, it's a little harder to see. That's an A. And then I alpha going the other way. Okay? So how are we going to do this? We're going to first say, I'm going to just show you this as opposed to working through all of it, since hopefully you can try it on your own and then just kind of look at the solution. But let's talk about it. So we start off with our diagram. We know A equals R alpha. We know that for a slender rod, it's 1/12 m L squared. So L being the entire length. And again, we want to be in meters, so it's 0.9 meters. And there's our particulars. So we know that our R distances can be 225 millimeters. So if we go ahead again, where do we can take our moment about? We're going to take it about C, because that's where our reaction is. So we need to get rid of those two because we have no way to solve for them yet. So we take the moment about them to eliminate them. And then we go ahead, like we'd expect, the distance P from C is half the bar plus the R bar equals I alpha plus MAR. Combine them. And in this example, I left things in symbolic form and just went ahead and threw. And this is essentially down here is just a algebraic um, consolidation of what we saw up here. So nothing. And if you like it better to use all numbers, by all means. But this kind of helps see where it came from. So once we get to this point, we go ahead. We know 75. Let's put it back. So 75.45 plus 225, which is the total distance of the moment. And that's just going to equal my mass, 4 kilograms, times this thing in here, 1/12, the total length squared, plus R bar squared alpha. So we go ahead, we get alpha to be 107.1. And now we have to find our reactions at C. All right. So what do those reactions look like? Very similar to what we did before. We go ahead for the reactions and looking at our diagram, we again sum the forces in the y. We know Cy minus W equals 0. And why is that? Because remember that our acceleration was all in the x. So we didn't have a y acceleration. Okay. So then that just becomes what it would be static, 39.2. And then we do some of the forces to the right in the x equals minus max. And I did this just for sign convention, but we get cx minus p equals minus max. The only trick here is just remembering to put in r alpha for your acceleration. We solve it, we get negative 21.4 Newton. So what that means is that our reaction in C is going to the right. Okay. Okay. So I hope that helps. And uh, that should make sense. And now I want to do one more that's a little more challenging. Just to be clear on this, um, is you can think of it as when we actual look at the actual bar. The bar has a force down here of P, and it has a force P, and then it has the acceleration. So this is what I meant to say. Sorry. Um, so we can think of it, this is my CX and this is my MA. That's what, so this has to be going to the left in order to balance that. So if I misspoke earlier, I apologize. Okay. So look at that, and it has to balance in your sum of the forces equals MA equation. All right. Okay, now this one's a little more challenging, but we can definitely get through it. In terms of this, so what do we have? You can write the particulars down, pause and do that. But really what we're trying to do is we want the acceleration of the carriage and the acceleration of point A, given a known amount of force, 4 pounds, that is pulling it to the right. So again, it's going to be one of those instantaneous things, as with all of chapter 16. So we're going to combine a few things we already know and go ahead and solve. So here's what our objects look like. So we have the weight of B is 6 pounds, the weight of A is 16 pounds, radius of A is 12 inches. We have a 4 pound force. If we divide the weights by 32.2, we get 0.4969 slugs and 0.1863 slugs for A and B. So we want to find acceleration of B and the acceleration of point A. All right. So if we look at our diagram, now before I draw anything, um, we're going to need I. We know I is going to be for a circle, because it's the only thing rolling is A. It's going to be 1/2 m of A r squared. So this is anytime you have a cylinder. Okay, in 2 dimensions, it'd just be a circle. But my cylinder. Sorry about that. Spell check piece of paper. So go. So cylinder. So 1/2 MAR squared, and that equals 1/2 0.4969 times times 1 squared. And why 1? Because the radius is 12 inches. So everything has to be in feet. So sometimes find myself remembering and going back to that. So we end up with this equal to 0.2490 pound second squared foot. So make sure you write this down since this paper's going to disappear. Now, one thing, this is maybe a little hard to see, but the acceleration of A with respect to B is just equal to alpha R. So the reason to think about that is that as this moves, this rotates. And so what's it going to do? If I pull this way, then we're going to say that is it the whole thing, if it rotates, it's going to rotate like that as it moves. Now, whether it goes that direction or not will depend on what we get in our final answer. But nonetheless, we can relate that the essentially the acceleration of A to B by alpha R. Okay. So that relationship comes from that. Now, um, so we're going to use that to say that acceleration of A relative to B is equal to acceleration of A minus acceleration of B. But we know that this equals that, which equals that. So we're going to write then that this equals or goes to alpha equals the acceleration relative to B. I'm sorry. A relative to B over R. Now, of course, I didn't need this intermediate step to get that, but we're going to go later and we're going to substitute in this for this. Okay. So um, if you have questions about that on Friday, we can talk about it, but that's going to be something, of course, that makes things a little, if you don't recognize that right away, makes things a little more difficult. So you have to kind of think about what's actually happening. As I pull this wants to roll along. So relative to each other, it's just that. Now, we need a free body diagram. And of course, we know We have two wheels. Now, no dimensions, so we're just going to write this as N1, N2, weight B, and of course, the weight A. Again, the exact location is not important. And then on this side, we'll have, of course, MB, acceleration B, going that way. And we'll have our cylinder with I alpha and M A, acceleration A. All right. So what are we going to do? So first thing, let's sum the forces in the X equal to MAX. Now, that's going to be for this whole thing. So what's that going to look like? Well, the only force is P, right? Sorry, P. So it's going to be P. Actually, P belonged over here. Sorry about that. There. So P's over there. So P equals MA AA plus MB AB. Okay. And that's not so bad. So then that's going to be 4 equals 0.4969 acceleration A plus 0.1863 acceleration B. So I've just substituted in the respective masses. So we're going to come back to this equation later. So I'm going to put a 2 on it. I think that's what I did in my notes. I'm going to be consistent. Where 1 is, we'll find out shortly. Now we go down to our circles. Perhaps I should have drawn those a little closer. Go ahead and draw a couple of circles. So these represent the cylinder A. All right. Now for A, we know it's going to have weight of A. All right. And that's our point C, our instant point of no point of rotation. And then we have our force, friction force. Okay. Now, we always have a friction force, even though we're not told friction, because otherwise it wouldn't roll forward. It would just sit and spin. So in order for anything to roll, it has to have some kind of a force here. And we will talk about that more in class. And then we have MA of the center of gravity. And IG times, or IA, because that's what it is, also G times alpha. That's what we look like. So if I sum the moment about C, then if I call this point C here, then there are no forces, right? We agree. All of them go through there. So if I sum the moment about C equal to I in general, IG plus MAD perpendicular, then that's going to look like what? 0 equals IA alpha. This is I alpha, sorry. IA alpha plus MAAA times R. So there's my equation. So now got to do something with that. Okay, so now recall that we said acceleration of A relative to B, we know equals AA minus AB. So we also knew that acceleration of A relative to B equaled R alpha, which we talked about earlier. So we can also write that alpha equals acceleration of A minus acceleration of B over R, can't we? Basically substituting in this and then solving. So divide that by that, we get that. All right. Now, if we go back to our equation here, right, then we can rearrange that because if we substitute in acceleration A, we can go ahead and we can write this as 0 equals IA bar times acceleration A minus acceleration B over R plus mass acceleration A times R. Okay, so that's our relationship that we have. So think of it as this was formerly what? It was the it was alpha, right? So alpha is this. So we've just substituted that into there. And then, of course, this is my MAR. So nothing's changed. All right. So now I can rearrange things and I get this equal to IA over R plus MAR all times acceleration A. So all I did, sorry about that, all I did was I took this over that plus that, and I basically factored out the acceleration A. And then this AB over R, I made into minus IA over R times AB. Okay, so this AB over R was this, and then multiplied by that. So you can see that IA times AB over R is that, and this is this. So it's basically just algebraic combination. So, but the nice thing about doing that is now what I can do is I know that IA over R is simply what? Well, we determined that IA is 2490 pound second squared foot all over 1 foot. So of course feet cancel. And MAR is what? That equals 0.4969 pound second squared per foot times foot. So of course the feet cancel. So of course we have the same units, right? So divide that, multiply by it, we get the same units. Now what we can do is, and I should have probably called this equation 1, but anyway, now what we can do, and again, this is nice that you can go and rewind, but we can take our original equation up here, the 0, right, equals this. And what do we know about that? Well, we've defined IA R as this, and we defined MAR as that. So what does this become? 0, right? So bring that down here. 0 equals IAR, which is this, 0.2490, right? Plus 0.4969, right? And then all of that is then just multiplied by respective values. So let me fix this. So times acceleration A, and then that's going to be minus this, which is the same value, right? Only now it's 0.2490 times acceleration B, right? So again, all I did was substitute in and remake that equation, which ultimately it reduces to 0.7458 acceleration A minus 0.2490 acceleration B. Okay. Now, I also have the original equation, right, up here, this one. So notice that you kind of see where I'm going with this. I know that 0 is this equation, And if I hold them side by side, you can maybe I'll slide them up so you can see. This was my original equation, 0.4969 plus that, right? That came from this piece. I went through this process, went through all this. I got that. So now I can bring in the the equation I showed you just a second ago, this one, and that equals what? 0.4969 acceleration A uh, plus 0.1863 acceleration B. So now I have these two equations, two unknowns. I solve them and I'm done. So it turns out that the acceleration A gives me 3.79 feet per second squared. And acceleration B is 11.36 feet per second. And that's it, just like that. Okay. So it seemed more difficult. Most of it's for algebraic manipulation. This one thing with the relationship of the I alpha, this one here, that's probably the trickiest part. So, but that's hopefully gives you a better sense of everything. So that's where we're at for this. And again, the lectures I'm posting are a combination, but they're meant to cover last Friday, Monday, and today, Wednesday. So apologize this didn't come out sooner. Uh, I'll be back on Friday. Thanks, everyone, and I'll see you soon.